Hello, everybody. This is Professor Ma, and this is the introductions on the sections on equations of planes. Two items are important for these sections. I want to bring it back. First, the dot product, and that is if u and v are two vectors, and to establish that they are perpendicular, it's the same as saying that the dot product is zero. Okay, and the second thing that in three dimension we have cross product, and the cross product of u and v, if I will call that w, then w is perpendicular to both of them. Okay, in particular, the cross product of u is first u is equal to a, b, c, v is equal to d, e, f. Then the cross product is this little formula I, j, k, a, b, c, d, e, f. Determinant of that. Okay. So, in other words, this is how we produce a perpendicular vector W, which will be important in these sections. Okay. So bear in mind with these two formulas we're going to use, and we'll proceed with the equation. Okay. The equations of planes in three space corresponds with first degree equation, linear equations, and these are pictures of linear equation with one variables only, and the other two variables are missing, and these are basically constant planes, and here are drawing of these planes defined by a single variable. Okay, let me see how the, okay, if I have a variable that's missing, well, I'm skipping example, coming to this one first. In this case, the x is missing, and what we do to draw the plane is we first draw the equations in the yz plane. We set x0, and we graph this line existing in the yz plane, and it looks like a line like this. And this is the yz plane, and I draw this line at 0, 0, 2, 0, minus 4, 0. Okay, the x is 0. And then on the other hand, since the x is absent in the equation, so the x values can take some any value. So in other words, any point on this line, I can move along the x directions, change the x value over here, and set it to be any value I want to be, and the result is going to be these slider planes generated by that line. So this is how we graph plane with the missing variables in the equations. It's parallel to the axis of the missing variable. And finally, we come to how do we graph a a variable, all three variables there. Then the way we graph the plane is we graph the intercepts. So for example, here it's an equation of x and y and z all present. So I set two of them to be 0 to figure out what's the intercept on the other, the last variable axis. Okay, so we do that, and we apply points and draw this little triangle, and then you can imagine what the plane looks like, how it sits inside this three-dimensional space. So this is basically how we visualize the plane, by playing around, drawing, see where it sits. Okay, and now of course we want to do the opposite. That is, we want to describe position of planes, and then we want to recover the equations of the plane. And the way we do is the following things. We to specify in three-dimensional space, in two-dimensional space, in the plane, back to lines, and to figure out the equation of a line, basically I need two things. I need a slope and a point. This is too deep. We're going to do something very similar to that in 3D, but instead of the slope, we're going to use actually the normal to the perpendicular direction of the slope. But in this case, it's going to be a vector. So what I'm trying to say over here is to specify a plane, all I have to specify is the perpendicular to the plane. So if this is a plane and I want to specify the equation of the plane, and to get a measurement that to specify the direction of the plane. Let me say that. Okay. Which way is the plane facing directions? Well, we'll say it's facing the normal directions. You think of a handle, put a handle on it, and that handle is pointing in normal directions. That defines the direction the plane faces. Then you need a point. Okay, there are a lot of plane that faces in that direction. Then you need to say, oh, I want this plane facing that direction, but I want to be at that point. Then you have to move the plane over there at that point. And this is what we're going to do. Okay, so a normal vector is a plane, a vector perpendicular to a plane. And suppose we're given a point P in the normal vectors, and this is where we're going to use a dot product, okay, to derive the equation of the plane. Suppose I have another point XYZ, go below XYZ on the plane, any other plane, any other point. Then the vector connecting the point to the XYZ cube, that vector must be perpendicular to the normal. Hence, the dot product must be 0. I write that in the equations, and that's the normal dot with the vector PQ. Remember, the vector PQ is the point Q minus P. So it's X minus R, Y minus T, Y minus S, Z minus T. And voila, I got equations, or we call point normal form of the plane. In 2D, we have a point slope. In 3D, we have a point normal. The normal is perpendicular to the plane. Okay, and actually, yeah. So this is slight variations on the point slope form of the line in 2 dimensions. Okay, once we have this, then we can figure out there's many standard questions or we can talk about the specified planes, and we want to find the equations. So therefore, the way to go about finding the equation of plane, we will go after two things. Normal. What's a normal? Get a normal vector. 2, get a point on the plane. And once we have those two things, there's a formula. Dump it in, and that's it. Okay. So here's an example. Okay, so here's a normal, here's a point, and just dot them 0 and clean it up, and that's the equations. Okay. And so this one's easy. And now we're going to hide information a little bit. Okay, and we say, okay, fine. Okay, here are two parallel planes. And I want the equation of the plane parallel to this one, but contains the point P. Well, the first thing you need to do is you want to find the equations of, so the first thing you want to do is you want to find a normal. And what is the normal of these equations? If you think about it, the normal must be 2 minus 3, 1. Okay, this must be the normal, because in order to get these equations, it must come from these sets of equations produced like that. It fixes the the coefficients. Okay, anything normal to the plane has the coefficients ABC, and these ABC tells you what the normals are. So in this case, the normal is 2 minus 3, 1. Okay, and once I know the normal for this plane, this must be the normal for the other plane too. Then I can put the point normal form to figure out the equation of the other plane. Okay, what else? How do we find the equation of 3 points? 3 points make a plane, except when they line up. If they all sit on a line, then there are many, many planes go through them. And here's a picture of such a, if I can find it. Here, there's a line, and if I have 3 points on this line, then there are many, many planes pass through them. Okay, so in this case, we say these 3 points are collinear. That's the line up. But if I have 3 points that's not collinear, that they don't line up, then they will define a plane in space. So if I say that. So those 3 points from a little triangle, then they generate a plane. How do I find the equation of the plane? I need a normal. How do I get a normal? Here are 3 points PQR, and if I look at a vector PQ and PR, I take the cross product. The cross product is perpendicular to both PQ and PR must be a normal. So hence you take the cross product, and that's a normal. And once you have a normal, you use any one of the point, and you use the point normal equations form and to get equations. Okay, that's how we find the equation of 3 points. The plane containing 3 points. Okay. And this is obvious. We can justify how whether equations like these are formulas for parallel planes by looking at their normals. And if the normals are in the same directions, 1, 1, 1, 2, 2, 2 are in the same direction, and 3, 3, 3 is the same direction, different length. But if they are the normal of a plane, then those planes are parallel. Okay, so these 2 planes have parallel normal. Well, one is the multiple of the other, so therefore this plane must be parallel. Okay, let's talk about lines a little bit more in free space. When we say parallel lines in space, we not only requires that they don't meet, usually in 2-dimensional space, on a plane, a parallel line is they don't meet. But in 3 dimensions, this is not enough, because in 3 dimensions, we could have something called skewer line. That is 2 lines like that, they don't meet, but they're not parallel. In order for them to be parallel, they has to be like that. They have to sit in the same plane. Okay, and that brings up, we can find another question about plane. That is, if I have 2 skewer lines, there's only, think about it, there's only one plane pass through this line. Okay, that's parallel to this one. In other words, there's a plane here where this line kind of go underneath. You think of this plane as an ice sheet, and think of this as a submarine or something goes underneath, parallel to it. There's only one plane. And which plane is that? That plane is done by do the following things. You take your line. This line gives one direction. This line gives one direction. Put that together. Go this direction, that direction. This is the plane they generate. Okay? Take that plane you generate, you move it up to where the original line position is. So that plane is a parallel plane to the plane you want. So we have these questions. Okay, first, here's a question that justifying two lines are skewed. Okay, and the way we justify and say, oh, they have different directions. Okay, and so then they couldn't be parallel. They couldn't be in the same plane. Okay, since one point that way, one point that way, and that will have to justify they don't intersect. So you try to say supposed to intersect, and you will wind up with a system of equation with two letters but three equations, and these three equations couldn't be satisfied. Okay, there's only so this is a contradictory equation, so there's no A and B will fit all three. So therefore, it's impossible to have meeting points with all three components are the same, meaning they don't intersect. Okay, so this is how we justify these two lines. First of all, are skewed. The next question is the one we about the parallel planes. Okay, and now let's find the plane containing the line L, but does it intersect the line N? And again, we need a point on the plane. We need a normal on the plane to the plane. And think about what a normal is. That plane was formed. Remember, we have two directions, right? Skew lines. That plane is formed by taking the plane that generated by these two directions of these two lines. That means the normal must be their cross product. In other words, the normal is perpendicular to both of these lines. Okay. First of all, we get a point by, say, arbitrarily plugging 0 to obtain a point on the plane L. And the second, we obtain the normal by crossing these two directional vectors. And once I have a point and the normal, we plug in the equation, we get it. Okay. And then another demonstrations of using the normal vector is we talk about the angles between two planes, and those angles between two planes called dihedral angle. Actually, there are two of them. When you have two plane meetings, like such, and there's an angle on this side and this angle on that side. Okay, and so the angle between these two planes, and usually the smaller ones called the dihedral angle. Of course, then there's a bigger ones, 180, the complements of that. Okay, how do we figure out the dihedral angle? If we think about it, oh, by the way, the dihedral angles is measured by find a point V on the line of intersections, and then find the point B such this is perpendicular, right angle, and then find a point A on the other plane and such that this is also perpendicular. Okay. And then that angle is what we call the dihedral angle. Notice if these two points, if B is here, if A is over here, and if I draw an angle from V to here, and that angle in the space, that's a different angle. That angle is a lot smaller. Okay. So that's how the dihedral angle is measured. If you think about it, the dihedral angle is the angle between the normal. Okay. If I have normals like that, and let me draw this picture a little bit. I suppose I put a plane like that, and it's just two plane. Then this is easier to see that the dihedral angle are two normal. They're the same thing. In other words, if I have two planes intersecting like that in space, I can always rotate them, and so you can see it directly line up with intersections like that. Then you can see, oh, the angle they make between this and that is the same as a perpendicular angle between them. You just, the angle was like that. You're just not measuring the perpendicular angle, just shift 90 degrees. The two normal, just shift those two edge 90 degrees. So therefore, the dihedral angle is the angle between the normal. And we have the angle between the normal is the using the cosine dot product formulas. The cosine theta of the angle is the unit dot product of the unitized. Okay, so in that I will get the angle. Okay, and so that's it. So this is briefly introduction to the sections on the equations of planes and normals and normal vectors. Very important. Okay, the basis for a lot of things we are going to do about tangent plane. Yeah. Okay, that's it. Bye bye.